Good afternoon. Today we will say more about interrupts. This is the role of an interrupt in a computer system. We have a system bus which contains data bus, address bus, and control bus. I believe that all of you have passed some computer architecture course or similar. So those elements are familiar. CPU does not cooperate in serving the interrupts. It does not cooperate directly with device controllers. There is a special circuit called interrupt controller that arranges handling of interrupts. So let us look how typical cooperation of processor with controller is performed. CPU programs some operation to be done in the controller of the device. For example, to read a sector from the disk. It needs to provide the address in memory of the data to be written, the number of the sector on the disk, the direction of the transfer, if it is reading or writing, or all those data are put to the controller when CPU orders the operation from the controller. And the controller starts to execute this operation. When it is done, the controller issues an interrupt to the control bus. There are many interrupt lines in computers, from 4 to, it's unlimited, I think. In Intel processor, the interrupt controller can accept up to 256 interrupts. But typically the number is smaller. The controller can send the interrupt to CPU or not, depending on current state. When it decides, what happens? Oh. Okay. When the controller decides to send the interrupt to CPU, it is single interrupt line. No, not one out of many. It is single interrupt line, and it sends the specification of this interrupt when CPU sends the acknowledgement. I am ready to accept this interrupt. So the controller sends the specification, which contains number of interrupt line on which the interrupt was reported, and some data from the controller, typically. CPU makes a jump when it gets the interrupt number. A jump to the interrupt handler. It's just a procedure. Typically, it is contained in a device driver. So it executes this procedure. When it is completed, CPU sends the information of end of the operation to the controller and the interrupt controller. This finishes the interrupt serving cycle. Let's look closer inside interrupt controller. It is built of several registers and some combinational circuits. Red lines are in active state. Green one, yellow ones are passive state. Green lines are not directly connected with the interrupt. So we have 3 lines in active state and 1 in passive state. I do not say 1 or 0 because in many computers the interrupt's active state is 0, not 1. So it's better to say active state than 1 or 0. Okay. First register is just to synchronize interrupt signals that come to the processor in asynchronous mode to synchronize it with local clock. So the role of this register is limited. This is very important. This register is interrupt mask. Mask ends active states of interrupt lines with internal value. So those 2 are allowed to go through the mask. This one is not allowed because it is 0 here. Only those 2 can be accepted. The encoder selects which interrupt that came through the mask has higher priority. This one. This is the lowest priority, so this is the highest priority of those who came through the mask. Its code is 10. It is 0001 1011. So it is 10. It is sent through the data bus of the computer, the number of the interrupt. Additionally, there is a gate, OR gate, that sends the interrupt signal to the processor. If any of those lines in is active state, AND gate transfers it to the collective mask, global mask. This is very useful register because it allows to disable or enable all interrupts in a single step. When we enter 0, all are enabled. Of course, only those that have 1 in mask are allowed. If we enter 0, all are disabled. Finally, this signal comes to the processor. When the processor sends an acknowledgement, it automatically clears the collective mask. So when we accept an interrupt, all interrupts are disabled automatically. And new mask is entered to the mask register. This new mask is prepared by the encoder in advance. Typically, the new mask, masks the line on which we accepted the interrupt, and all with lower priorities. After some time, let's assume that the processor unblocked the global mask programmatically, and a new interrupt came with the highest priority. It is enabled. So it comes to the mask, and now the encoder sends to the processor the code 11. And interrupt signal on the interrupt line. Again, when the acknowledgement comes, clears the global mask, and now all interrupts are disabled because this that was accepted and all with lower priorities. After some time, special command tells interrupt controller that given level was finished of interrupt handling, and it unblocks the mask and so on, but we will not deal. These are the details. Finally, if all interrupts are served, the mask should be all ones. Let's look what happens in software when we send the interrupt. We have some process. It has some past instruction, current instruction, and next instruction stays here. So we execute current instruction. The processor accepts interrupts only between instructions, not in the middle of the instruction. So we finished instruction and the interrupt is accepted. The acknowledgement is sent to interrupt controller. The processor, when it accepts the interrupt, automatically saves the interrupt vector. What is interrupt vector? It contains at least two registers, typically two registers. Program counter to return here in the program in the future, and flags. They are automatically sent to the process stack. And now the processor makes a jump. Here, in fixed position in memory, is the service table. Every level of interrupt has entry in this table. So interrupt number is the index in this table, and we make a jump to the location appointed by given entry in this table. If it's interrupt number 2, we take the cell number 2 from this table. Here is the interrupt handler, and let's look what it does. It saves the state of the running process. What is saving the state? It stores all the registers, all other registers, because two of them are already on the stack. It sends the rest of registers on the stack programmatically. Interrupt vector is stored automatically by the processor. The rest is stored by instruction that stay here. It's series of push operation. Push one register, push second, push third, and so on and so on. When we saved the state, now everything is safe. The current state of the process is entirely saved on its stack. So we enable other interrupts to come, because it can happen that during serving the interrupt, another interrupt comes of higher priority. So we enable interrupts. In Intel processor, this instruction is STI. And the handler does some operation which is planned to perform during the serving of the interrupt. Finally, we must finish. So, for the time of restoring the state, we disable all interrupts. In Intel, it is instruction CLI. We restore the state. Restoring the state is popping back the registers to physical registers. And finally, the instruction IRET is executed. IRET is interrupt return. It does almost the same as return from the function, return instruction. It does some additional things. Namely, the program is run in program status. Interrupts are served in system status. So we should switch between system and user state. When we accept the interrupt, the processor automatically changes to system state. IRET loads from the stack the return address and switches from system state to user state. So it is almost return, but some additional elements. And two registers are popped. Return pops only the trace. Interrupt return pops flags and trace. Those two registers are typically stored automatically. And that's all. So please tell me, based on last week's lecture, what is under number 3? What action is performed while we are serving the interrupt? Typically, of course, there can be some exceptions, but what is typically done when the interrupt coming from the device comes and is served? What is done here? I told it. In concurrent operating system, when we order some operation on hardware, the process that orders this operation is suspended and other process is run. So, in interrupt routine, we resume this process. Here, operating system checks what process waits for this interrupt and resumes it. That's all. There are some special interrupts that are served differently, but typical interrupt coming from the device is just waking up the process. And we can execute next instruction in our process, because the trace is restored and the trace contains the address of this instruction. We will, of course, many times return to this scheme, but at the end of first slide set, I will show you the reference model of operating system on which I will enumerate the functions of layers of typical operating system, because many times we will refer to this layered structure. On the bottom, there is microkernel. Microkernel of operating system is responsible for splitting set of physical processors to a number of virtual processors for every task in the system. So this magic of running new processes, of when the new processes are born, is here. More, it allows to communicate and synchronize between processes. So if we have some basic synchronization primitives, they are realized in microkernel. Third, this is first. First is parallelism. First function of microkernel. Second is serving the interrupts. All interrupts come through microkernel. Microkernel gets the interrupt, saves the process state, and directs the serving of interrupt to the correct driver. So if we return to the previous slide, what happens? Maybe low battery. So here is the jump from the kernel to the interrupt to the device driver, which is not shown because it is not important. It plays only organizational role. So here we have in the kernel, here we jump to the device driver, we return and finish the serving the interrupt in the kernel. Device drivers are just over the kernel. They organize the data exchange between the processor and devices, and they serve the interrupts, the device interrupts. There is a layer of buffers. It's kept in systems from historical reasons. Nowadays, we have large cache memories inside devices. A disk has very large cache inside. So the role, it is kept because there are operations to borrow and return some buffers. So other layers of operating system assume that this layer is. So it is kept by the role. We will not discuss this layer because the meaning of it is mainly historical. A file system. Here we have physical transfer between processor and memory and devices. Here is a logical structure that we impose on data on the devices, file system or other organization. Program supervisor, different names are used, like housekeeper or others. there is a layer that controls the programs. When we run a program from a program, when we send a signal to the program, when we check the status of the child process, all this is done in this layer. Memory allocation for programs, for new programs that start. Here we have some software that is not part of operating system, but it is kept in memory longer than single program runs. They are runtime systems called middleware for database management, for network systems, sharing devices between nodes in distributed environment, for graphical systems like Linux. It does not have graphical interface itself. We must run it. So it runs as runtime system. And on the top, we have user programs. Okay. So in next slide set, we go deeply inside a kernel. This is outline of the topics we will discuss. The name of kernel is somehow misleading because before Unix, the kernel was what is called nowadays microkernel, a basic part of operating system that deals with interrupts and concurrency. But when Thomson and Ritchie issued Unix, they were not computer engineers, they were computer users. They gave name to the system Unix kernel. So it was ambiguous if we talk about the smallest part of operating system or the entire operating system. So a new term, microkernel, was established. But I will use the same name, kernel, in both. I will use both terms in the same meaning of the smallest part of the operating system. It is responsible for task control, synchronization of tasks and devices with tasks, and interrupt handling. The basic property is establishing concurrency. We have concurrent run of processes even if we have a single processor. It is done inside a kernel. We organize parallelism using the operation of context switch between context of one task and another task. We can imagine that we have a number of tasks. A task is used as a common name for processes and threads. Some operating systems are based on threads, some on processes. So to specify that we talk about something that runs parallel with others, we call it task, and such a name is used in the literature. So we have 3 tasks, and every task has its own set of registers. This plugin is set of registers, but not physical registers. They are values of registers of given task. We select task 2 to run, so we plug in the registers to physical registers of the processor, and the task starts to run. The task switch is saving the registers of one task and restoring the registers of another task to physical registers. Such is done the context switch, just exchanging the registers between tasks. The task context can be understood as entire set of entities required to run this task, like memory pool assigned to the task, some devices, maybe virtual resources, and in a detailed view, we call the context only the registers, only that part that must be stored when we switch between tasks. So during task switch, we leave the data in memory where they were. We do not touch them. We also leave the data in device registers, in device that are allocated to the task. But CPU registers will be necessary for running other tasks, so we must save them somewhere. 3 places for storing registers are used. In some IoT processors, there is a second set of registers. So one set of registers for user state and one for system state. And if we have only one task, it's quite typical in IoT, then we simply switch between system and user without storing the context. It just stays in the second pool of registers. However, in typical multi-task system, we must store, and it is stored in task descriptor or on the stack, typically on the stack. All the task descriptors are collected in some data structure inside the kernel, which is task table. Every task is described in its own entry. There is some ID of the task, an owner, a parent, and a list of children of this task, resources allocated to a task. All is described in task descriptor. And one of most important fields in this descriptor is a state of the task. From the perspective of the kernel, 3 states are important. There can be more states. In Unix, the state graph is highly complicated. But from the kernel point of view, there are 3 states important. Running is a process that occupies the processor. So running process or running task has registers in physical registers of the processor. Ready has everything needed to run except processor. So we can run it every time when the processor becomes free. It is ready. Stopped or suspended, there are many names used. The task that waits for something else in addition to the processor, for some condition, for given time, for memory allocation. It can be quite large set of possible events. But there is an event which potentially wakes up this process, and then it becomes ready. Here we have example descriptor table, in we have some number of tasks and one descriptor 3. We can run a new task in this descriptor. It has special field in use 0. That means that it is free. In this system, we have 2 processors because 2 tasks are current. They are running. So we have 2 processors. 2 tasks are ready and 2 are suspended. This is another snapshot. We have 3 processors and 3 current tasks, 1, 3, and 4. Every current task has some processor on which it runs, and 2 ready tasks that just wait for a processor, and 2 suspended tasks. How the tasks are chosen to run? There is a special kind of kernel called scheduler that just chooses next task to run. It has some internal policy of priorities, of observing the process properties. Now we do not discuss them, we discuss them later. But this procedure at the end just selects next task to run. And because inside a procedure called in the kernel, the set of ready tasks can change. For example, we accept the device interrupt, which wakes up a process waiting for this interrupt. So when we had k processes ready, after this interrupt, we have k plus 1 ready. And we must choose between old processes and one new process. So the scheduler is called at the end of every kernel operation. We call the kernel, regardless if we do it programmatically or by interrupt. Programmatically is using interrupt as well, but it is just software interrupt. And at the end of serving this interrupt, a scheduler is called. For example, when timer interrupt is served, typically it's the end of time slice for a process. So next time slice probably will be allocated to another process. Oh, this we discussed already. And this is the scheme of serving the interrupt. Some task runs. It orders some input-output from operating system. Operating system starts the device, and scheduler chooses some other process to run. An interrupt comes. It wakes up the kernel. The kernel here wakes up the task that was suspended, and it chooses this one or this one. scheduler is called and it chooses which task to run. Oh, I describe it. This is how the task switch is performed. We have task P1. Its registers are in physical registers. An exception comes. So registers are pushed on the stack of this task. And a scheduler, I assume that the scheduler decided to switch from task P1 to P2. And now we restore the registers of P2 from its stack to physical registers using pop operation. And final two registers, which form the interrupt vector, are restored using iret. So we see that the interrupt calls to switch to the kernel, and the kernel performs iret to other process that was interrupted. So between storing registers of one task and restoring registers of the second task, some procedure of the kernel is executed. It may be intentionally called by this task. For example, this task calls the operation wake me up at 3:15. And the kernel suspends the task until 3:15 is on clock. I assume that it is in the future. And another task is chosen to execute. And finally, in this operation, the scheduler is called. In typical operating system, the interrupts are prioritized. That means that an interrupt of higher priority can interrupt handling of the interrupt of lower priority. That's why at the end of storing the state of the task, we had enable interrupts instruction. When the task state is successfully stored, the interrupt handler enables interrupts to let interrupts with higher priorities be served. So storing the context and restoring the context is protected by disabling interrupts. But between them, there are some operations performed in the driver or other procedure that are performed on the interrupts enabled. Oh, here we have some history. Here we have the time axis. What happens when two interrupts come one after another and the second is of higher priority? We run the task, and this is the top of the stack of this task. Here an interrupt comes, so we save the task context under disabled interrupts. So task context is now over the previous top of the stack. And we serve interrupt P1. Now second interrupt comes with higher priority. So we save the context of serving P1 on the stack. This is the context of serving P1 and start serving P2. We finish serving P2. We restore the context of P1, so it's taken from the stack, and finish serving P1 interrupt. So P1 is partially here and partially here. After finishing P1 service, we restore the context of the task from the stack, so now the top of the stack is as before. However, we know that it can be another task. So we need not save the state of interrupt handler on user stack because we don't know if we return to the same or the other stack. Every task has its own stack, and we can interrupt the task with stack S1 and return to the task with stack S2, and we need not store serve the interrupts using the user stack. So for this purpose, we have separate system stack. Every task has its own stack, and additionally, we have a system stack. The second reason why we should not serve interrupts on a user stack is that there can be many interrupts. Simply, we do not know how many are there interrupts. Do you know how many interrupts are in PC? I know, but perhaps you don't know. 16. But the controller, the structure of Intel controller accepts up to 256. Only in the architecture of PC, the designers decided to use 16 interrupts. And every handling procedure, of course, they are prioritized, and every procedure can interrupt one of lower priority. So we can have active, potentially, 16 handlers, interrupt handlers. They must store the context, and maybe they make some additional pushes of some data. We don't know how many room of our stack we should reserve to successfully serve 16 interrupts. So for those two reasons, only the task context is stored on its stack, then we switch to system stack. It shows user stack and system stack. It is user stack on which the task runs. It's the top of the stack. We accept interrupt P1 that saves the state of the task on its stack and switches to the system stack. We serve the P1 interrupt, and second interrupt comes. It saves the state of P1 service on system stack, because current stack is now a system stack. P2 is served, It restores P1, it takes this record from the system stack and finishes serving P1. And here it restores the same task or some other task. This task has different color. It is the stack of different tasks. So here we switch from system stack to this or to this one. Who judges which one? The scheduler. The scheduler runs here on this line and chooses next task to run. And we restore the state of this task, which will be next one to run. But our computer can have many processors. And the kernel can be not parallel. What means that the kernel is not parallel? We prohibit the kernel to run on two processors at the same time. For example, when we have two system calls from two tasks on two processors, one system call comes to the kernel, the second waits in a loop for the first to finish. When the first finishes, it enters the kernel. There are many such kernels. However, there are kernels that allow parallel calling of kernel procedures. They can run in parallel, of course, with some exceptions. Some parts of operations cannot be in parallel, and in such a situation, we have active waiting. But it's seldom. So we need as many system stacks as we have processors, because every processor is executing some procedures using a stack. And if they run in parallel, they must have separate stacks. So we have as many user stacks as we have tasks in the system. There may be user tasks and system tasks. In modern operating system, many tasks are internal to operating system. Oh, it's easy to imagine. For example, we cancel the file. The file occupies large space on a disk. So the user gets the response OK immediately, and some system process adds the areas on the disk to list of free areas independently. Just process got the result OK and continues. And system process frees the disk space occupied formerly by the file. This is an example. Okay. Now we know how the tasks are arranged and how they run in parallel or virtually in parallel if we have one processor. We call them concurrent because they can interleave in time. We can run a part of one task and part of second task, again one task, so we switch the processor between. So they run virtually in parallel. How to start a new task? First, we need a descriptor for this task. So if task descriptor table is full, for example, it can be limited in size, we cannot start a new task. We assign the state of a new task ready, not ready at once. maybe typically it gets the state new created because we must allocate memory to this task to run it. So maybe some intermediate state of being started or similar. It can be first task in a program, or tasks can clone. It's typical, like in Windows, that we can start many tasks in a single, many threads in a single program. So we allocate memory for the task if it is a first task, it is run together with the program. If it is next task, we must do some memory allocation, but limited only for the task stack, because we need as many stacks for threads as is the number of the threads. When we start a new thread, we must cut some memory from the program memory and allocate a stack for this thread. Perhaps from the computer architecture course, you know that when we run a high-level language program, the memory on the stack are organized in stack frames. Yes? You know stack frames. Stack frame is typically created by the calling subroutine. Calling subroutine arranges a stack frame for the called subroutine, and it is finished by the called subroutine because some operations can be done only by callee. So the caller allocates the frame and fills partially the frame, and callee does the rest, so fills the rest of the fields in stack frame. Who creates the first frame? You know, languages like C. It starts in function main. Who creates the frame of main? Yes, the kernel, not exactly. The last element of the kernel, operating system, let's say. In our hierarchy of levels, it is created by the program supervisor, some higher level of operating system. You are right. Only operating system can create the first frame on the stack. We can call the program with parameters. Okay? The parameters in C are argc and argv. Who puts those parameters on the stack? Operating system. Operating system knows how we called this program, what parameters we entered in the line in which we run the program. And operating system makes a string in memory of the program, and the pointer to the string is argv. Oh, argc. Argv is argv is pointers to the parameters. Argc is number of parameters. Okay. Okay, we have the stack and rest memory if it's the first task in the program. So we should start the program. How we start the program? We build on the stack the set of empty registers and perform IRET instructions. We return from the interrupt. That never happened. Every jump from kernel to a program is done by IRET. So on this, we build the initial frame of the program of main function. We put on the stack zeros like the context of registers, and we perform IRET to this program. And after IRET, just the program runs. So how to terminate the task? First, what is the reason that we terminate? It is some interrupt. It can happen that the program called the syscall terminate the program. Every program has such a syscall at the end, entered by the compiler. So at the end of main function, there is a syscall terminate. But a program can be cancelled by its parent using kill in Linux. It can be terminated because it executed illegal instruction. It's internal trap in the processor. It's kind of interrupt, discovering illegal instruction, or using memory out of memory allocated to the program, memory overrun. It's another type of interrupt. So every closing a program is some interrupt. Oh, another example. We limited the time that program can run. So on every timer, system timer tick, we check if the program run over this time limit or not. If it run over, we close this interrupt. We close this program inside the interrupt service. Every end of program is inside some service of some interrupt. So we deallocate memory if it is the last task. Oh, some errors close the program unconditionally. For example, if you have illegal instruction, all tasks in this, all threads in this program are closed. Not only this one that caused illegal instruction. So if it's not last one, we deallocate its stack. If it's the last one, or we close the entire program, all the tasks at the same time, we deallocate entire memory of program. What else? We free up the memory, yes. We close the files open by this program. So we just clear the situation. And finally, we just deallocate the record in task descriptor table. And we will not return to this program in the future. It is just closed. And the descriptor of these tasks becomes free. Oh, what happened? But I did not tell you the truth. Because typically, in typical operating system, even when we close the program, we give the program a chance to clean the situation programmatically before we close this program. Of course, when we close the program intentionally, we can do it in the code. But if it's done on the call from the parent, we don't know when this call will be issued or if it ever be issued. So A typical situation in which we close the program is giving the program a chance to clean up or even to ignore the killing signal and continue. Of course, it is advanced programming, but the mechanisms are. There are situations when we must close the task externally. For example, when the stack of the program is corrupted, we see that stack pointer points out of the program. So returning to this task, every program wants a stack to run. When the stack is corrupted, it cannot perform even several operations. So we must close it externally, but it is seldom. It is just emergency operation. Typically, we let the program close itself. We do not close the program. We ask the program to close the program by itself. How it is done? Of course, if we need to give a program a chance to clean up, we must call some function in the program which does it. So every program, you can look in the documentation, for example, in C or C++, every program has linked library procedure closing the program. And using special code, we can cover this procedure with our own procedure. We have a table of reasons of closing the program. They have specific numbers. And every such level in this table is connected with the pointer to some procedure. We can change this pointer to our own procedure and do what we want to do when the closing signal comes from external. For example, separate for illegal instructions, separate for terminating by parent, several of them, about 20 as I remember, maybe more. Some of them are predefined that cannot be covered. They are critical errors. But most of them can be covered by user own procedure. And in this procedure, we can either perform our own cleaning operation, like closing internet connections, writing the files that are kept. There is a mechanism of keeping files in memory. So we can write the image of the file back to the disk. Just some cleaning operations and then to finish, or to ignore, to restore the erroneous situation inside the process and continue. Let's look how it happens. We have current subroutine. This is the code of this subroutine. So this is some frame on the stack. This is code of the function in code area of the program. And as I told you, we have linked to the program some special procedure terminating the program. Normally, it is not called. It is called on special situations. So when we have the order to terminate the task, I told you, it is always some interrupt, illegal instruction, call by parent, whatever. It is always decided in the kernel. And in the interrupt, interrupt vector is pushed on the stack. Interrupt vector contains program counter and flags. Program status word is flags. And of course, this program counter points somewhere to the code of current procedure. It's obvious. And the kernel starts with saving the context of the process on the stack. So we have saved context. And we switch to the system stack. For technical reasons, this interrupt vector is repeated on system stack. We'll not come into details why. For technical reasons, it is copied on system stack. And kernel subroutine starts to run using the system stack. So it is the frame of the kernel procedure. It moves the top of the stack upwards, making some room here, and enters a new frame on the stack. This frame has the trace, the previous program counter. So we can return to this procedure if we want. Because in the trace, we have the current address of this address. So if we just go to the end of the cleaning procedure, we return to the program. But it is artificial. This trace is entered by the kernel, not by the subroutine call. And the program counter on system stack is changed to this task termination procedure code. So if we return, if we perform IRET, we will go back to this procedure rather than to this one. So we start executing, it should be the beginning of this procedure, the code of the beginning of this procedure, not in the middle. So this procedure can decide to terminate the program or not. If to terminate, it cleans the situation and issues the extra code terminate. If we choose no, we fix the situation and return from the cleaning subroutine to the subroutine in which the interrupt occurred. That's all. Okay, we terminated the task, or maybe we suspended this task because we called some input-output. And we have lower number of tasks than we have processors. What process to run? We have 3 current tasks, no ready tasks, 3 processors, and one of those tasks decides to terminate. What to run on this processor? Who knows? What is nothing? What is the life of a processor? Taking the instruction, loading the instruction to the processor, executing, and loading the next instruction. You are right. Some processors can. Not all processors. Especially those processors that have a power saving mode, in which we can stop the processor. Okay, but in every operating system, we have some processes just to waste the processor time. They are called idle. You are right. Some of them, or all of them, can change the processor state to sleep. But it is not done by the kernel. The kernel runs a process, and this process executes sleep operation. Or not, if this processor does not have such an operation. So we have special idle tasks. When we have two current processes or tasks, no ready tasks, so we have idle tasks. And here we choose one of idle tasks to run on this processor. And it can sleep the processor, you are right. In some systems, those tasks do some useful work. For example, if the system is safety critical, those tasks check the internal operating system structures if they are correct. And they perform early alarms if something runs, but runs to some wrong situation in the future. They check integrity of operating system. There is an error in this slide. What is the error? Having 3 processors, we need 3 idle tasks, but we have only 2. It can happen that all processors are free. So we need as many idle tasks as many we have processors. Oh, it discusses just what you said, that some processors have special instruction to stop the processor. The processor is not entirely stopped because the circuit that checks if the interrupt came is online always, because we can escape from this sleep state by interrupts. Okay, so it is just on this halt instruction. This is about parallelism in the kernel. I think that it is better to return to this material when we first discuss the general rules of parallelism. So I will stop this slide set at this point, and we will return to this slide set after synchronization. Okay. Oh, I have special slide set on. Do I have this here? Maybe not. Oh, I can download it from MS Teams. Oh, now I will show you some structures that are in Phoenix real-time system. Oh, it's Polish version. Yes. Oh no, only the initial slide is in Polish. The rest is in English. It is to let you get more familiar with Phoenix because it is the system that you will use in labs. It is Phoenix runtime system, Phoenix real-time system. Where I have a pointer. Here you see the logo of Phoenix. It is the operating system with microkernel because some operating systems are monolithic. They have integrated everything in a large operating system. Nowadays, it is seldom. Most operating systems are based on microkernel. The interface is compatible with POSIX, but not fully. Some system calls are not possible, but generally it's compatible. It works, it's free, so you can use it for free. It's used commercially, especially in water meters, in electrical energy meters, in gas meters. So it is used in Europe and not only in Kazakhstan, in many countries, in IoT. It's open source, so you can even modify it, and you will modify the system. You can modify it and compile. You can change the process management in the system. What you will do, you will change the scheduling in the system in one of the tasks. You can change memory management, which you will not do because I do not know it well enough to prepare a lab task for you, but maybe in the future. You can change everything you want in the system. And my advice is in IoT is one of best systems that I use. So if you build some IoT system, you can use it freely because it's open source. We will discuss in our lecture what is the structure of stack frame of a task because it is important in the context of operating system. So I will not describe why. These are the fields. Maybe briefly, I'll describe what is the structure of stack frame. This is a stack frame of a function, which calls some interrupt, which performs some syscall. It is important. It is important how it is built because sometimes it holds some parameters for the kernel. and how to access those parameters. It's important. So this is the structure of the frame. This is the calling subroutine. So in the program, we call from this subroutine, we call this subroutine. It is called underscore syscall. Calling subroutine puts parameters on the stack. It is created by some macro, which passes as parameters a number of syscall in the system, because they have a table of codes, and a server number. Because the structure of microkernel is that typically it accepts a syscall and directs it to some part dealing with some set of issues. For example, memory management, file management, and others. Some system calls are served by the kernel itself, because they are related to inter-process relationships. But most of them are directed to the servers. So we have function number and server number. And some structure in which the server, the kernel procedure, can put an answer for us here. Some languages reserve a field for result of the function on the stack. Most modern solutions use registers for the result of the function. But elder solutions pass the result of the function as the field in stack frame. Here we have the trace, the return address. Those three elements are created by the caller function. The callee, the called function, creates the dynamic link to the calling subroutine frame, because it will load the frame pointer with its own frame address, not to lose the frame pointer to the calling subroutine. It saves it on the stack. It is called dynamic link. We will tell more about this when we will discuss the structure of the stack. Here are other elements, like local variables and work fields. I don't know if syscall has some work fields. And finally, this function performs syscall. Syscall is software interrupt. In Intel, it is the instruction with mnemonic name int. Every interrupt stores on the stack what? Interrupt vector, the trace, and flux register. So here we perform the extra code, the syscall, and current values of stack pointer is top of the stack, which is here. I assume that the stack grows to lower addresses, which is in Intel. In Intel, stack grows to lower addresses. And frame pointer points to over the dynamic link. Do we have time? Yes, a little. So we have user processes that are running user programs, P1, P2, P3. And we have special code for initiating kernel operations on call from processes. Every syscall directs the control to this extra code reception code, which judges what to do. Typically, it's a function call that is directed to system functions. Most of them are in servers. Small number of them is inside the microkernel. For example, if we want to send a signal between two processes, it is done entirely by the kernel. If we want to open a file, it is directed to a file server. This part is generated by this macro that creates a syscall. This part of the stack frame. And return address points to the code because it's the address of the calling function. And frame pointer and stack pointer point to the stack. Something happens to my equipment. After the syscall, we have all parameters in process address space. The dispatcher chooses the function call, and it has accessible both process address space and kernel address space, which is not accessible to the process. But to the kernel, it is available. So parameters of kernel call are somewhere in user process, somewhere here. They point to this area. And every system call is by the dispatcher directed to given server, file server, memory server, or your own server. One of your lab exercises will be build your own server and enter it to the kernel. So system function is taking some data from process address space and filling some record called message. It has nothing to do with distribution. It is called message, but it is just memory field. The dispatcher fills the parameters, those ampersand m, number of server, number of function. It fills as some package. Oh, I don't know what happened. Oh, I see that we should finish. That we will discuss how the parameters are passed to the kernel procedure on the next lecture. Okay, so thank you for today.